let me remind you that we last time we discussed alternating series, okay? And just to remind you what alternating series test says. So remember, we needed to assume these two conditions. This was very important for us to be able to guarantee convergence for an alternating series. And this is a statement that if you have a series that's alternating, then this is going to converge if the following conditions are satisfied. So first, you need your sequence AN. So ignore the plus or minus. Just take absolute value, if you will, to get rid of the negative signs whenever available. Make everything positive. That sequence has to be monotonic, non-increasing, so the terms have to be going down. Okay. And second, we also need the limit of AN to be equal to 0. If these two conditions are satisfied, then we can deduce that the alternating series converges. Like, for example, the alternating harmonic converges because AN is 1 over n in this case, and the limit is clearly 0 and it's decreasing. So conditions are there. In this case, number 2, it diverges. First of all, notice that we cannot use alternating series test here. It is alternating, but one of the conditions failed. Okay, the limit is equal to 1. It's not equal to 0. So that means that the alternating series test does not apply. We cannot use it. However, because of this, we can now use divergence test. Because if this limit is equal to 1, then that means that this sequence here is going to be oscillating. It's going to be getting closer and closer to two values, positive 1 and negative 1. Okay? So the limit does not exist. In particular, it's not equal to 0. So you can use divergence test to justify that the series diverges. Okay? So if you have a problem in which you need to determine whether you can use alternating series test or not, what that means is check that these two conditions are satisfied. If one of these conditions is violated, then you cannot use alternating series test. You need to do something else. Okay? Now we know that if number 2 fails, then you can deduce divergence because then divergence test is going to tell you that it will diverge. If number 1 fails, meaning that your sequence is now monotonic, non-increasing, so it means that either the sequence is constant or is going up, right? So let's see. Well, no, this cannot be constant because then it will be non-increasing. So the sequence is then increasing, right? The terms of the sequence are going up because AN itself is positive and the terms are getting bigger and bigger and bigger. That means that the limit cannot be 0. It's either infinity or something else, but you are moving away from 0 as you go deeper into a sequence. So then again, if number 1 fails, you can use divergence test to argue that the series will diverge. Okay? So basically, if you want the alternating series to converge, we better have these two conditions. Okay? If one of these fails, then ultimately the series is going to diverge, but you need to justify by other means, which in this case would be divergence test. That's what we discussed last time. And then I kind of mentioned the notion of absolute convergence and so on. But before we get into that, let me give you one result that we get immediately as a corollary from the proof that we did of the alternating series test. Okay? And this is the one that allows to estimate infinite sums, at least in the case of alternating. Then later on, I'm going to give you another theorem which actually involves the integral test, and then this would be our 2 ways of approximating infinite series. Okay? So what do I mean by this? What do I mean by approximating infinite series? Well, suppose that you have a series, okay? So let AN, and of course, if we want to approximate this infinite sum, it doesn't matter. I mean, it doesn't matter where we start, whether 1, 0, or whatever. But if we want to approximate this infinite sum, that means that we know already that this converges, right? If the series diverges, then what are we approximating? So let AN be a convergent series. So we have a series that converges, okay? So we know that this is equal to something. If this sum equals something, okay? Be a convergent series, then the sum is equal to S. The idea is that you want to know what this S is, even if this is not one of the series that we are able to calculate precisely, like geometric or telescopic, okay? So we want to get as close as possible to this value. So one notion is, well, after all, this is the limit of Sn, right? And we know the limit of Sn equals this number. So if you pick n big enough, with the partial sum, you should be able to get closer and closer to what this value is, okay? So as a notion, so let AN be a convergent series, then it has a sum. We may approximate S by Sn, which is a sequence of partial sum, right? Remember, this is a1 plus a2 all the way up to an, okay? And this, then, of course, we do this for n large enough. What we want to make more precise today is what we mean by this, okay? How far do we need to go? So how big this n has to be so that we get the desired accuracy. So we can approximate S by the sequence of partial sum as long as we consider enough terms in this sum. This is hopefully clear to understand. Now, the moment that you approximate something, there is always an error involved, right? This thing is not the same. Sn is not the same thing as S, because S is the limit of this as n approaches infinity. Do you understand this? Now, what's the error that we make when we approximate S with Sn? The error is given by the difference of these two quantities, right? The actual value is something that you don't know, then you approximate by something that you know. The difference is the error that you're making. So the error in this approximation is, let's call it En, and by definition, this is S minus Sn, right? And the point is that the smaller this error is, the closer Sn is to S. So if this number is close to 0, then Sn is close to S. Do you understand this? So the smaller the error is, the better is our approximation. So our job is to try to minimize this error. So the question is, can we find a way to control this error? Let's say that I want an error less than 0.001. This will guarantee an accuracy of 2 decimal places in the approximation. If you want the error to be less than 10 to the 4, then you are guaranteeing an accuracy of 4 decimal places when you do the approximation. Do you understand this? So the question is, can we control this error? Well, in the case of alternating series, we can. That's the theorem that I'm about to present. Okay? If the series is not alternating, on this, all the conditions, you can do something else that we will talk about later on. Okay? So, but this is a general thing what I'm writing up here. For any series that converges, it equals to some sum, to a certain number. You want to know what this number is or get close to it as much as you can look at the sequence of partial sum with n big enough, and then you need to understand that if you make the approximation, there is an error involved. The question is, can we control it? Okay? So, remark, if the series is alternating, then we can control this error. Okay, so I'll give you the theorem. So this is the alternating remainder theorem. So alternating remainder theorem. And here is what it says. And I'm going to give you the theorem, and then I'm going to give you the idea of the proof, and that's the reason why we need this first sentence. It's going to be very clear once we justify this. So suppose that you have a convergent alternating series, and we need the condition, the following. We need an plus 1 to be less than an. This, of course, you know that this is going to be guaranteed anyways, right? Because remember that you need this sort of monotonicity if you want the sequence to, if you want the series to converge, okay? So if a convergent alternating series satisfies the condition that an plus 1 is less than an, for all n, an plus 1 is less than an, for all n, then the absolute value of the remainder, so the absolute value of the remainder en, will define what this is above. This is what you get when you look at the difference of the actual value minus the sequence of partial sum. Involved in approximating the sum S by Sn is less than or equal to the first neglected term. So in other words, what I'm saying here is that the absolute value of En, which equals this is going to be less than or equal than the first term that we ignored. So what is the first term that we are ignoring? What is Sn? We have our infinite sum, and then we're saying, no, I don't want to add to infinity. I'm going to cut the sum right here up to this point, okay? I'm going to add these numbers, and whatever I get, I'm going to say that that's my value. That's the approximation that we're making. What's the first term that we are ignoring?
AN plus 1.
The AN plus 1. That guy is an upper bound for the error. So our error is going to be less than that next term that we are ignoring. Okay? That's what this theorem is saying. So this is less than or equal to AN plus 1. Okay? So that's a statement. And let me give you the idea of the proof. So I don't have to get into too many details, but with this you should be able to see why this is true. So, the point is that S, what is S equal to? S is going to be equal to A1 minus, so A1 minus A2 plus A3 minus A4, and so on, right? Is your infinite sum. And then let me write here, plus or minus AN. The reason why I write plus or minus is because, depending on what N is, it could be a positive or a negative. But then the next one is going to be minus plus. Do you understand the minus plus? Because what I mean by this is, if this guy is positive, then the next one is negative. This one is negative, and the next one is positive. Okay? And plus or minus, minus plus, and so on. That's what the actual S is. However, our Sn, I'm using capital N, so let me put capital N. So our Sn, what's Sn? It's just up to here, right? A1 minus A2 plus A3 minus A4, all the way up to our AN. Okay, that's what Sn is. If I now subtract, what's going to happen? That the error, which is S minus Sn, what is this equal to? If I subtract the top line minus the bottom line, all of this piece cancels out, right? So we are left with the tails, the terms that we are not looking at, that's the error, right? The stuff that we are ignoring. So what is it that we are ignoring? We are ignoring minus plus AN plus 1, plus minus AN plus 2, and so on. Let me try a couple more. AN plus 3. Etc. So this is the tail, so this is what we are ignoring. What I want to show is that this right here is going to be less than or equal than this first number. Okay? And, here we're going to play exactly the same game. So let's see. We need to do two cases. One in which the first one is a negative, another one in which the first one is a positive. Okay? Because there are two possibilities here, depending on the n that we pick. For case one, that's the case in which we have negative AN plus 1 as the first term, okay? As first term in, for En. So in this case, what do we have? So then it means that En is going to be equal to negative AN plus 1. And now that means that the next one is a positive. So I'm going to play the same game that we did before. So we have plus AN plus 2 minus AN plus 3 plus AN plus 4. I guess let me do one more. And so I'm going to place parentheses like this. And because we have the monotonicity property, again, just like last time, this is greater than 0, this is greater than 0, etc. So what do we have? We have a negative number, right? And then this negative, because this, remember, without the minus is positive, so this is really a negative number. And then we're adding positive stuff to it. What happens when you take a negative number and you add positive stuff? You get big, it gets bigger, right? It gets bigger. So it follows that En is going to be greater than or equal than negative AN plus 1. We okay with this? All right. So, okay, so we have this. And then I guess we could also, then from here it follows also, of course, that minus En is less than or equal than AN plus 1. So multiply by negative 1, right? You have to flip the direction of the inequality. And then we get that minus En is less than or equal than this one. we good? Okay, but I like the first one, so we're gonna stick with this one. Now let's do the same thing, but what if the first term is positive instead of being negative? So the other possibility would be that an plus 1 is the first term of en. So in this case, we have that en is an plus 1, then minus an plus 2 plus an plus 3 minus an plus 4. I guess I should do one more, an plus 5, etc. So as we did last time, I'm going to keep the first one alone. I'm going to factor out a negative, and then you can rewrite this as an plus 2 minus an plus 3. Okay, and then this would be plus an plus 4 minus an plus 5, and so on. And the point is that once again here we have positive stuff because of the monotonicity. So this big parenthesis is positive, and now we have a positive number minus something positive. So whatever this is going to be less than this guy. Yes? So en is going to be less than an plus 1. So moral of the story, if we pair the two highlighted conditions, what do we have? En is greater than, and if it's less than, particularly if we say it's not equal to. So we can say, so en is greater than or equal to minus en plus 1, and then is less than or equal to an plus 1. So it's between those two numbers, okay? So here is en, so we have that is greater than or equal than an plus 1, that is also less than or equal than an plus 1. What does this mean? This means that the absolute value is less than or equal than a plus 1, okay? Because that's what it means. It's between this number and it's negative, so when you take absolute value, it's going to be less than this one, okay? So that's why we did the proof last time, because the idea here is exactly the same, so you will understand what I'm doing here. So anyways, the important thing here is the statement, and the statement hopefully is pretty easy to remember. So you cut at a given point your Sn, and you decide to approximate your series with that final sum. Then the question is, what's the error that you're making? Well, just look at the next step. The first step that you ignore, that's your power. Your error is going to be less than that. Okay? This is one example. So, a natural question is, like I said here, for n large enough, the approximation, you can approximate. In other words, you have a reasonable approximation. So the question is, okay, how big should n be if you want a desired approximation? Let's say that we have a series and we want 3 decimal places. How many terms do we need to consider until we guarantee that? Okay, so let's do a problem like that. So let's see, what is my series? This guy. So example, consider the series. So let's say that we have the series from 1 to infinity of -1 to the n plus 1 over n to the 4. That's a series, right? And then let's see, who can tell me, does this converges or diverges? It converges. Why? No, this is an alternating series.
Right.
This is not a p series.
The limit approaches 0.
This is an alternating series. Our an is 1 over n to the 4, and then that an is decreasing, and the limit is 0. The condition is satisfied, so it converges by the alternating series test. So consider this series. So certainly it converges by the alternating series test. Yes? So, and I want you to approximate this sum. So let's try to approximate this sum with 3 places of accuracy. So approximate the sum with 3 decimal places. of accuracy. So basically what I want is, I want the error, I want it to be less than 0.0001. Okay? That's what it means to have decimal places of accuracy. So the real value minus our approximation, when you look at the difference, we need to get something less than this. So that means that at least the first 3 decimal places, they are matched, right? Maybe at the 4th place, they're not going to match, but at least here we're guaranteeing that these 3 decimal places are matched. You understand this? Okay. So how do we do this? Well, the idea is, okay, we need to know, basically the question here is, what should be our n? Where do we make the cutoff in the infinite sum? Where do we cut it to guarantee that we have this approximation? And what's going to tell you this is the term that will be less than this number. So if you guarantee that you have a term that's less than this number, and you made the cutoff right before that one, you know that the error is less than this number. If it's less than this, then you're good to go. Okay? So let's do it. Solution. We know that the absolute value of En is less than or equal than An plus 1. Okay? So that's the theorem that we have above. So what you do is, let's declare I want this to be less than 0.001. And then the question is, find n. Okay? So what n will guarantee this inequality? Again, the theorem tells us that the error is less than or equal than the first term that you ignore when you made the approximation. Therefore, you want to force this term to be less than this. You require this. And now the question is, what is this n so that this happens? Okay? Once you find it, then you are in business. So now we go to our formula. So remember, an plus 1, so note our an is 1 over n to the 4, okay? You forget about the plus or minus. So that means that an plus 1 is going to be equal to 1 over n plus 1 to the 4. And we want to make this less than 0.001. At this point, to solve this inequality, you do it however you want. In this case, we can solve it manually. When the inequality looks too complicated, don't stress too much about it. Just start picking values of n. N equals 1, n equals 2, n equals 3, until you get a number that satisfies this. Okay? So you don't have to stress too much about it. Anyways, but what if you need 20 terms? Then you're going to be doing that 20 times. So if you have a smart way of finding n, it's better. Okay? If not, then just start picking values. Okay, here this is something that we can easily solve. So I move the n plus 1 to the other side, and I divide by 0.001. Okay? So 1 over 0.0001 is going to be less than n plus 1 to the 4. So that means that my n plus 1 has to be bigger than the 4th root of 1 over this. So remember, 1 over this is the same thing as 10 to the negative 4, right? This is, no, 10 to the 4. Okay, so this is 10 to the negative 4, okay? So 1, 2, 3, 4. So this is the same thing as 10 to the negative 4. So when you move it to the other side, here you have 1 over 10 to the negative 4. This is just 10 to the 4, 10,000. Yes? So the 4th root of 10,000 is 10. So that means that I need n plus 1 to be bigger than 10. So what is n? What is n? 10. It has to be bigger than 10, right? So n is equal to 10. Or I guess if you want, you can say n is going to be bigger than 9. So the first n that satisfies this is 10. Yes? And you know, if you want, you can check and just plug in, because that's a strict inequality. Let's see, if we pick 9 and we put it here, we're going to have, we have 1 over 10 to the 4. For n equals 9, you have 1 over 10 to the 4, which is exactly this number. We have equality. We don't want equality. We want it to be strictly less than. So you need to move 1 step forward. Okay? All right. So n equals 10. So that means that the actual sum, so S, we can approximate it by S10. Okay? And what is S10? So S10 10 is going to be, so we start at 1, and the first guy is possible, right? So that's going to be 1, and it's 1 over n to the 4. Let's look here at the sequence. So it's going to be 1, this n equals to 1, minus 1 over 2 to the 4, plus 1 over 3 to the 4, minus 1 over 4 to the 4, plus 1 over 5 to the 4, and then minus 1 over 8 to the 4, plus 1 over 9 to the 4, and then minus 1 over 10 to the 4. So if we add these terms, right, these 10 terms that we have here, then we know that whatever value we are getting here, this number is going to be an approximation for the actual infinite sum, and it will be aggregated with, 3 decimal places of accuracy. So I calculated this. I mean, you can do this if you want on your own, but I calculated this, and this is going to give you 0.946993. Okay. And the reason is because, the fourth power, it grows, but it doesn't grow too fast. So that's why we needed up to 10 terms to be able to decide this accuracy. That would have been like a factorial or something that could have like this. Probably with 2 or 3 terms, you already get the accuracy that you need. And then you can actually add it manually nicely and so on. Okay. But this gives you an idea. So you can get several problems with this. You should have seen this already in the homework. There are some homework problems that they tell you, okay, you have this sequence of partial sum. Let's say that I ask you to approximate this with S5. Find a bound for the error. What would be a bound for the error if we approximate this with S5? Well, 1, 2, 3, 4, 5. We're going here, so the bound for the error is 1 over 6 to the 4. So whatever approximation you're making is going to be less than the first term that you're ignoring. Do you understand this? So those are most of the questions that you have in the homework. But then you will get questions like this one. Just a series approximated with this accuracy. You need to find the n, and then you need to do this. Or I may ask you, what n do you need to get an accuracy of whatever? In this case, 3 decimal places. Your answer would be, in this case, my n is 10. Do you understand? Okay. All right. Questions? Do you understand how to approximate alternating series? It's really easy. What you don't understand? It's really easy. Ask so that I can explain.
I didn't get the last part where you explain. Did you just explain about the homework, what it's going to ask us?
If I ask you to approximate S with S5, so question.
Yeah.
Find the error. Find the error in the following approximation. What's the error? Just use a theorem. The error is bounded by, so find, when I say find the error, I mean find an upper bound. Find a bound for the error in this approximation. So what does the theorem says? The error is bounded by the first term that you ignore in the approximation. Do you understand that statement, that sentence that I just said? Okay. What's the approximation that we're making here? What is this? It's A1, in this case it would be A1, minus A2, plus A3, minus A4, plus A5. Yes? That's what the approximation is. So, by the theorem, the error is less than or equal than what? An A6. And what is our A6? 1 over 6 to the 4. Which is 6 to the 4. That's 1 over 1,296, which is, oh, look at that, that's nice. This is about 0.00077. All the stuff. So, for example, right here already at S5, we're already guaranteeing our 2 decimal places. It's just that I wanted a 1 here because you see this 7 here means that probably the 4th decimal place will be a large number, and then you want to round, it's not going to be nice and so on. But for sure, for example, you have 2 decimal places already with the first 5 terms. Okay? So if you're happy with that, you don't need to go and look at 20 terms. If you want 20 decimal places, then you need to look at maybe thousands of terms. Who knows? We have to calculate that here. Okay? But it's pretty easy to use. That's why I'm saying it's not complicated at all. It's the error is bounded by whatever is the next term that you're ignoring. That's all. Okay? You need to understand what you're doing here. Instead of looking at the infinite sum, you're looking at the finite sum. Which one? Stop here. Stop at a 5. If you have a 20, you stop at a 20. And what's the error that you're making? Well, the next term that the first term that you're ignoring, that's the one that tells you what's there. That's it. You okay with this? All right. Questions? Okay. Again, you have a couple of questions like that in the homework. This is the kind of question that they ask. Okay. Let's see. Before I move on. I mean, if you understand the definitions, this material should not be hard at all. But you need to understand the definitions to be able to recognize these problems and do them quickly. Let's see, let's take a look at, okay, so right here, this first question, let's do this one. So for this series, calculate the sum of the first 3 terms, S3, and then find a bound for the error. Okay, so this is an alternating series. Yes, this series converges because your AN is 600 over N to the 0.9, right? So that's certainly decreasing. At some point, when N is big enough, this is going to start going down the terms. Yes, it's going to be decreasing, and the limit of this is 0. Do you understand this? So this series converges. Okay, so because this series converges, then we can use the remainder theorem. So let's go ahead and do that. So S3, let's compute S3. S3 is the sum of the first 3 guys. So it will be A1. So we begin with something negative, right? So negative A1 plus A2 minus A3. So let's compute that. Put it here on the board. So S3 is going to be minus A1 plus A2 minus A3. So when N is equal to 1, so we get 600, negative 600, and plus when N is equal to 2, we're going to get 600 over 2 to the 0.9, and then when N is equal to 3, we get 600 over 2 over 3 to the 0.9. Yes? Let's compute this. So let's see, I'm going to take out 600 from here. And then we're going to have negative 1 plus this minus this. I'm going to calculate that. Okay, so 2, so this is the same thing as 2 to the negative 0.9, okay? Negative 0.9, okay, got that, and minus 3 to the negative 0.9, okay, got that, and then I need to do minus 1, and then times 600. Okay, so I'm getting here, I mean, try to compute on your own also to see if you get the same thing as me, but I'm getting about negative 1,891.193,189. Yes? Are you getting this with your calculator, or you got something else?
I got close to negative 500, but I also didn't take the 600 out. I got something like negative 501, which
Negative 501. But did you use the 100 in all of that?
I I didn't move the 600 out yet. The 600 is still in the,
But that's
the
fine.
minor
That's
each
fine.
time.
So let me double check because I think this number is a little bit strange. So -1 plus 2 to the negative 0.9. Okay. Minus 3 to the negative 0.9. Okay. Times 600. Okay. Yes. I knew something was a little bit weird. So negative 501.692596. Yes? All right, so that's what I'm getting there. So let's put it here. So negative 501.692596. And then the error, so what's the bound for the error? So the error is going to be E3 is less than or equal than what term? What's the term? A4. This is exactly the next term that you're ignoring. We're coding here. The next one is my error bound. So what's A4? A4 is 600 over 4 to the 0.9. So 600, so let's see, I'm going to do 4 to the negative 0.9 times 600. So I'm getting 172.3. So 0.5. So at least make sure to include at least several places of accuracy. So 4, 7. Okay, I'm gonna put everything that the calculator gives me. So 172. I mean, in this case, this means that you need to go very far away into a series if you want to get a good accuracy. Okay, and it makes sense at the beginning. This is very slow. This is 100 here, kind of make the series delays its convergence a little bit. 75, 30. There you go. So what I want to tell you is, yeah, it's always good to get the green. What I want to tell you is, it's very easy to use this theorem. Okay, it's very easy. It's just, you do your sum, just make sure that you use the sum correctly in the calculator, and then what's the error? The next guy that you're ignoring. That's all. Okay. All right. Are we good? Okay. So that's Alternating Series Remainder Theorem. Let's go back here. And then let's talk about what I was mentioning before about absolute conditional convergence. So again, remember what's going on. So far, we know how to deal with series with positive terms. So when AN is always positive, we know how to deal with that. We have integral test, comparison test, right? Limit comparison test. We have several things that we can use for that. Then what if the signs start to behave, they are no longer positive all the time? The next case was, well, if they are alternating plus minus, plus minus, plus minus, then we know how to deal with that as well. We have alternating series tests. Now, what if we have a behavior that's irregular? Sometimes positive, sometimes negative. That's what we are about, what I want to discuss now. Okay? And just to have something in mind, just consider, I kind of pointed this out last time, so consider the following series. A series starting from, say, from 1 to infinity of sine of n over n squared. Something as simple as this. And let's say that we want to analyze the series. The point is that none of the theorems that we have discussed before will apply. You could still use divergence test, but the limit is 0. You use squeeze theorem here, and the limit is going to be 0, right? So divergence test does not tell you anything, and none of the theorems that we have studied before will apply because sine of n over n squared is not positive all the time, because sine is sometimes positive and sometimes negative, then positive again and negative again, and it's not alternating either. Okay, so consider this, then sine of n over n squared is not positive, or alternating. Okay, so none of the previous tests applies. So you could try the divergence test, but like I said, if you do a squeeze theorem, this is going to be between less than 1 over n squared and greater than negative 1 over n squared. They both goes to 0, so this limit is 0. Okay, so it may or it may not converge. So how to find its convergence? How to determine its convergence? And the point is that we need a new idea, because the ones that we have used so far, they do not work in cases like this. Okay, so what's the idea? Well, let's look at the series of absolute value, and let me explain why do we want to consider this. So consider the series. So to study, let me say here. So to study the sum of an, where an is sometimes positive and sometimes negative, the idea is, well, let's go ahead and let's get rid of this bad behavior and let's consider the series with absolute values. So basically what I'm saying here is, okay, you're behaving bad because of the sign, I'm going to make everybody positive. Okay? And let's consider the series of absolute values instead. So, by the way, there's a big difference. This is not the same thing as this. You understand this? The absolute value of a plus b is not the absolute value of a plus the absolute value of b. It's triangular inequality. This is greater than or equal to. No, sorry. Less than or equal to. Okay? Triangular inequality. So what I'm saying is, this is the case that we're looking at. I'm not putting the absolute value outside the sum. I'm making absolute value of each of the leading terms. Okay? So we're going to consider the series of absolute values instead. In other words, I'm making every single term positive. This way, all the terms are positive. So now, all the terms are positive. And this will allow me to then bring all the techniques that we have studied. Okay? So all the terms are positive. Now, why? Then the other question is, okay, let's say that we managed to deduce that this guy is convergent, that this one converges. Does that imply that then the original one converges? So that's a question that we need to answer. So the convergence of the series of absolute values, does that imply that the original one converges? Let's take a look at that. So note, assume that the series of absolute value converges. So let's say that when we do this, we do get a convergent series. Okay? Can we deduce something about the series AN? After all, this is the one that we're going to start, right? This. All right. So if this converges, then I want you to notice the following: that AN, if I have AN, let me not put this yet, and if I add the absolute value of AN to it, whatever n is, I don't care. I claim that this is greater than or equal than 0 all the time. Let's see, just think about it. This term is either positive or negative, right? This one is always positive because of the absolute value. So when this is positive, then this sum is going to be positive, right? Now, if this term is negative, what's going to happen to this sum? It will be 0 because they will cancel. If this is negative 2, then it will be a 2. Do you understand this? Because it's just the absolute value. So the point is that this will never be below 0. So if I consider this is certainly greater than or equal than 0. Yes? And also, AN itself is always less than or equal than its absolute value. If AN is positive, they are equal. If AN is negative, then it's smaller because the negative number is less than a positive number. Yes? In other words, this is less than or equal than 2 times the absolute value of AN. So if I replace this AN by its absolute value, then I will get something big. Do you understand this? Now, because this one converges, what can we say about 2 times the absolute value of an, it converges. And because this converges, now this series, this one here, is positive all the time, the terms. So we can use direct comparison test to deduce that if this one converges, then this one will converge. Yes? So we have that so far. So we have that the series an converges, then we have that inequality, and this is true for all n. So this one converges since the series of absolute value converges. And therefore, because we have this right here, okay, then by the direct comparison test, we have that this series will converge. Are you following the idea so far? Okay, so we have that this series converges. Now here's the other trick. Note, this is a nice trick. An, we can write it as an plus absolute value of an minus absolute value of an. Yes or no? Yes? Okay, so the series an is the same as the series of an plus absolute value minus this guy, right? So now I want to place parentheses in a strategic way. I'm gonna rewrite this as okay. What I'm doing is putting parentheses. And now the point is, why did I do this? Because now here we have the series of a difference of two sequences, yes? And we know that this one converges, this series converges, and this one also converges. That's what we just argued above. So what did we study in the properties? When you have two convergent series, then the series of the sum is the sum of the series of the difference is the difference of the series, right? That's one of the properties of series. So this now equals this guy minus this guy. But this converges. This one converges. So the series an converges. Okay? So moral of the story, if the series of absolute value converges, then our series converges. Okay? Then the series without the absolute value converges. So converging with absolute value is a very strong condition because it forces the original series to converge as well. Okay? So when this happens, we say that the series converges absolutely. Okay? So theorem, and what we just did is a proof of that theorem. Theorem is about the absolute convergence. Okay, so if the series of absolute value converges, then what can we deduce? The original series converges as well. Okay, so because of this implication, then this motivates the definition of absolute convergence. We will say that a series converges absolutely or is absolutely convergent if, when you look at the series of absolute value, it converges. Okay, so let me write that down. So definition. So whenever you have a question and they ask you to determine whether the series converges absolutely or not, what you need to do is look at the series of absolute value and check for convergence. Okay. So let an be a series. I'm not putting limits here because that means it doesn't really matter. Okay. That's why I'm not putting it starts at 1 or 0 or 20. It doesn't matter. So let an be a series. Then number 1. If the series of absolute values converges, okay, then, so we know that an converges, so we say that an converges absolutely. So it's said to be absolutely convergent. That's the definition, okay? Now, it could be, okay, it could be that the series an itself converges, but when you take absolute value, it does not. That could happen. Whenever this happens, and I'm going to give you an example in a minute. Whenever this happens, we say that the series converges conditionally. Okay? So this is a stronger condition, absolute convergence, because we're saying two things. We're saying the series converges, but when you do absolute value, it also converges. Okay? When you say converges conditionally, you're telling me the series converges, but if you do absolute value, it diverges. Okay? So if the series AN, now I didn't put absolute value, if the series AN converges, but when you do absolute value diverges, then it is said to be conditionally converged. Then AN is said to be conditionally converged. Okay. So an immediate example here is the alternating harmonic. So example, series from 1 to infinity of -1 to the n plus 1 of 1 over n. For example. Do you agree that this converges? This converges by the alternating series test, right? So this one converges by the alternating series test. But what happens when we look at the series of absolute values? Basically, by taking absolute value, all we're doing is we are removing this plus or minus behavior, right? So we basically get harmonic. Yes? And what do we know about this? It's divergence. So the original series, what type of convergence does it have?
Conditional.
It's a conditional convergence, right? It's not absolute, it's a conditional convergence. So this guy converges conditionally. Do you understand this? So when they ask you what type of convergence it is, this is the type of stuff that you need to do, okay? So if you know that it already converges, then the question is it absolute or is it conditional? Well, you have to look at the absolute values and see what happens, okay? If the absolute value converges, then you say it converges absolute. The convergence is absolute. If the absolute value diverges, then the convergence is conditional. Are we good with this? For example, if this would have been 1 over n squared, if it was a square here, then when you take the absolute value, I mean, it will still converge here, yes? When you take the absolute value, you will have 1 over n squared. And what do you know about that one? It converges, use a P series. So what type of convergence will we have in that case? Absolute convergence. Do you understand this? Okay. So now we're going to do a couple of examples, and then what's 5.6 about is just two tests that allows you to deduce absolute convergence. Because we don't have a test to deduce absolute convergence yet. If you want to check for absolute convergence, this is what you need to do. You need to look at the absolute values manually and then test that series individually. Now, there is a very nice test, it's called the ratio test, that allows you to immediately deduce absolute convergence. And we have a very similar one, it's called the root test, okay? So what I'm gonna do is, and that's what 5.6 is about, those two tests, okay? And the ratio test is gonna be very, very, with capital letters, important, but we're gonna do in the next chapter. And we talk about power series and so on, okay? So let me do a couple more examples here, and then I will introduce to you these two tests.
But in the test, will we do it like this or?
Exactly what you see that I'm right. I mean, you just argue, right?
Yeah.
What is it? Refresh. Tell me your question. Hey, sorry.
No, like when we do it like on the test, test 3, are we gonna do it like this, like we argued like with the different theorems that we did before, or are we gonna use like the test that we're gonna learn in 5.6 now?
Everything is on the test. You can use whatever you want.
Okay.
I mean, it's the same series. You can sometimes the same series you can analyze in multiple ways.
Yeah.
You take your pick, whatever you prefer. Right? That's why I told you take a page, Write down all the theorems that we are saying so that you know them, and then you know what to use depending on the problem. Okay? Because when I give you a series, I'm not going to tell you use this test or use this theorem. You have the series, you have to, just like when you have an integral, you need to decide what technique you use to solve the integral. I'm not going to tell you do it by parts or trick solve. You have to be able to recognize that. That's the same thing here. You see a series, what do? Convergence test, or is it alternating? What is it? Okay? And to be able to master this, what do you need to do? Problems. You just have to sit down and do problems. Okay? If you don't do problems, it's not going to be possible to master this. Okay? I already have the review done. I just need to put it on Blackboard. There are like 61 questions. Why? Because you need to do problems. If you don't do problems, you're not going to master this. Okay? And once you understand this, the questions, you can answer the questions like this, because it's not something super long that will take you 2 pages to answer. That's 2 lines. Alternating series test, here is the limit, it decreases, done. Move on. Or, convergence conditionally or absolutely, 2 lines. So these are things that you need to do, that you can do quick, but you need to know. And to know, you need to practice. Okay? So just do problems. Okay, so more examples. Let's see, determine convergence. If it converges, classify. By classify, I mean, is it conditional or absolute? Okay. 2s in classify? I mean, class is 2s. Classify?
Yes.
Yes? Okay. Classify. Okay, so let's see. Let me put, okay, I guess I already did the one over n, so I'm not going to look at that one. So I guess let's do this one. By the way, here is a silly claim. I claim that if a series already is of positive terms, if a series of positive terms converges, then it must converge absolutely. What do you think?
Yes. Yeah.
Why?
Because of positive terms is just absolute value.
So the absolute value is equal to itself, right? So this talk about absolute convergence is only relevant when your terms are not positive. When sometimes they are positive, sometimes they are negative, right? Because if everything is positive, then of course it converges. If it converges, it will do so absolutely, because an is equal to the absolute value of an. Does that make sense? So that's why we're talking about that here. Is it relevant only if we are dealing with stuff that are not positive all the time? Okay. All right. So let's do this one. Let's do. This one, and let's do. I didn't have this one written down, but let's see. I want to do this one. Let's do this. So this is natural log of n. Okay. So all right, let me. Do you understand that?
Yeah, just put like a curve from yellow.
And yeah, and let's see. I'm gonna put times. Let's do it like that. Yes.
Yeah.
Okay. All right. So let's analyze. Notice that I just said determine convergence. We do this however we want. Okay. For the series. Let's see this one. Number 1. The solution. So again, when you look at this, you need to have a feeling of what test you should be able to use. Again, the first thing that you should always do is try to see, just scan through it and take a look at the divergence test, but this limit is 0, okay? How do you argue this 0? You need to use squeeze theorem. But the limit is 0, so we cannot use convergence from here. We may actually see that sometimes it's positive, sometimes it's negative. So a good strategy to determine convergence is always take the absolute value and analyze that. Because if you get that converges, then you stop and you say converges, and it does so absolute. It's only when that diverges that then you go and investigate the series itself without the absolute value. Because anyways, I'm asking you to classify. So even if you tell me that the series converges itself, then you have to analyze the absolute value to see the type. So do the absolute value first, because you have to do it anyways. Okay? Only if that gives you divergence, then you move on. Okay? All right. So for this, we're going to analyze the series of absolute values. Okay, we're gonna go straight there. Now, notice that here, remember, the absolute value of a fraction is a fraction of the absolute values. The bottom is always positive, so the absolute value really is just the top, right? So this is just this. And now here, for this series, we can use all the tests that we know because everything is positive here. Okay, I'm gonna use comparison. So since the absolute value of sine is always less than or equal than 1, it's always between 0 and 1, right? Then if you divide both sides by n squared, the inequality stays because n squared is positive. So we have the absolute value of Sn or sine of n over n squared is less than or equal than 1 over n squared, right? What do we know about this series? 1 over n squared? It converges. So what can we say about our series? It converges by direct comparison test, right? So since this series converges, and remember, always justify. Why? It's a p series with p equals 2 bigger than 1, right? That's why it converges. Then, by the direct comparison test, we have that the series of absolute value of sine of n over n squared converges. So far, so good. But if this series converges, what can we say about the original series? It converges, but moreover, it does so absolutely, right? So we have here absolute convergence. Do you understand this? Okay, good. Questions about number 1? All right, let's take a look at the next one. So that's the sum from 1 to infinity of -1 to the n times n plus 1 over 2 or 3 to the n. Okay, so you may try to start writing down to see if this is alternating or not because of this, but notice that this is a little bit weird. In fact, this right here is a result of doing 1 plus 2 plus 3 all the way up to n. Okay, so this is not going to alternate all the time. But anyways, we are going to analyze the absolute value first, as I told you before. The absolute value is going to remove this behavior anyways. I don't care. Okay, this is going to become 1 when you take absolute value. And actually, just looking at it, when you take absolute value, that's not there, and that becomes a 1. What series are we going to get? What do you think about that series? It's geometric. What's R? 1 over 3. What do you know? Convergence. You see, those things, you do it like that. You need to have the practice, right? Once you do 10 problems like this, it's a 1 second answer. Okay? So, absolute convergence. So in here, we're going to consider the absolute value. Now, the absolute value, all it's doing is removing that -1 to that power and just making it a 1. That's all the absolute value is doing. Yes? So if you want, you can rewrite this as 1 over 3 to the n, just to make it more recognizable. And now, at this point, here you could put the limits, but it doesn't really matter the limits at this point. We're not looking for sum, we're looking for convergence. Okay? So now we see that this is geometric with r equals 1 over 3. It's less than 1. So what do we know? It converges. But if it converges, what can we say about the original series? It converges absolutely, or absolute convergence. Yes? All right. And then about this guy. No, that was from here. -1 to the n, and then this is a times over n. Can anybody tell me why I started at 2? Never done a problem starting at 2. So why did I?
Because ln of 1 equals 0.
Good.
Minus 1 over 0.
You know, I cannot begin at 0 because then this is not even defined. I cannot begin at 1 because then it gets 0, so it's not defined. So that's why I put the 2. It's not because.
Not to make our life more difficult. Save us some hassle.
It's just that I have to put the 2 or something bigger than 2. Okay, so we want to analyze this one. All right, so let's take absolute value, right? As promised, we consider the absolute value first anyways, because we want to identify the type. So the absolute value of this so this would be just this 1 over n times ln of n, and then we have to be able to identify what this is. Now this is positive, right? This is not a p-series. If you take the limit, you clearly get 0, right? So the divergence test is not going to tell us anything here. And then you may want to try to do some comparison or some limit comparison, but actually there is a very easy way that we can solve this problem. One thing that you need to remember is that we have the integral test at our disposal. So just look at that for a second and imagine, can you solve this integral? Is this an integral that you could solve? Well, yes, if I let u equals ln, my du is 1 over x, which would be right here, right? So it's a very easy integral to solve. So I'm going to use integral test. Okay? So I will use integral test here. The integral test applies because consider, so let f of x, so the corresponding function is, what's the corresponding function?
1 over x ln of x.
1 over x ln of x. So this clearly is greater than 0, continuous, and decreasing for x greater than or equal than 2, right? So from 2 to infinity, this function satisfies all the conditions that the integral test requires. Remember, the integral test requires continuity, the function to be decreasing, and to be positive on the interval that we care about. Doesn't have to be always, but starting at the point that we want, it must behave this way. And it does. So we may use the integral test. So in other words, when you look at a series, and if it satisfies these conditions when you make it a function, just, why would you do that? Well, try to see if something is that you can integrate. If it is, then you can analyze it that way, okay? Using the integral test. So the integral test says that instead of the series, we should look at the integral from 2 to infinity of 1 over x ln of x. And whatever convergence we deduce here will translate to the convergence of our series, right? Okay, so what's this integral equal to? So remember, we need to write this as a limit. Now here, let me find an antiderivative down here, so I'm going to do that. So the integral of 1 over x ln of x. So I'm going to let u be equals to ln of x, then du is 1 over x dx. And that's exactly what we have here, right? 1 over x dx, so that's my du. So this becomes the integral of 1 over u du, yes? And what's 1 over u? The integral of 1 over u? So this is ln of absolute value of u plus c, but u is ln of x, so this is ln of ln. Yes? The natural log of the natural log of x. So that's what we have here. So this will be the limit as b approaches infinity of ln of x, and then we need to plug in from 2 to b. So that would be ln of b minus ln of 2. Yes? So I don't worry about this part because this is just a number, but now what happens here? when b approaches infinity, ln of b approaches infinity, and therefore ln of something that approaches infinity also approaches infinity. So this part here approaches infinity, so that means this equals positive infinity. So what can we say about that improper integral? So the integral diverges. So what can we say about this series? So this series diverges by the integral test. Yes? Now, it was a series of absolute value. It does not mean that our series, the original one, will diverge. It just means that if it happens to converge, for example, what type of convergence are we going to have? Conditional convergence. And look, what's an here? So this alternating, yes? What's an? An is the positive version of the terms. So 1 over n ln of n, right? What do we know about that? The limit is 0 and it's decreasing. So what can we say about that series? Convergence, but the alternating series test. So what's the type of convergence? Conditional convergence. Yes? All right. Let me say here, but the actual series converges by the alternating series test. And indeed, our an here is 1 over n ln of n, and certainly the limit as n approaches infinity is 0. That's okay. And certainly n plus 1 is going to be less than an, because the bigger n gets, the smaller this fraction is going to get, right? Because this denominator is going to grow, and therefore the fraction gets smaller, right? So the two conditions are satisfied, so we can use alternating series test to deduce convergence. So the original series converges, but the absolute value doesn't, so the series converges conditional. So this is conditional convergence. Do you understand this? So, basically you take the absolute value, make it positive, use everything that you know from before. If you manage to get convergence, then you stop and you say your series converges, and it does so absolute convergence. If you get that the absolute value diverges, remember, that doesn't tell you anything about the original series. It just means that this one diverges. Now, if you have to analyze the original one by other means, and in this case it happens to be alternating, right? And then you can deduce conditional convergence. Do you understand this? Okay. So, but again, this seems like a lot of work to be able to deduce this. Can we have a test, something just like the integral test and the limit comparison test and so on? Can we have something nice that we can compute and immediately deduce whether the series will converge absolutely or not, and even will it tell us whether it will diverge or not? So thankfully we do, and in fact it's a very, very nice theorem. It's called the ratio test, okay? So let me write it down. I have written here an appendix because I knew that we were not going to have time for the proof, so put the proof here for you. But just to save time, let me copy here statement. So we can do some examples. Okay. So then later, if you want, you look at this page I call appendix, and then you can see the argument of why this theorem works. Okay. And if you want, you can ask me during office hours, and then I'll be glad to explain to you. But the important thing is that you have to be able to use it. Okay. It's actually, once again, very simple to use. So here is what the ratio test says. So let's say that you have a series. The only condition that we need is this. So this is a technical condition, but it's not too bad. We have to make sure that all the terms of the series are different than 0. And because the series is just a sum, if you have terms that are 0, just throw them away and get them out of the series. They do not contribute to anything, right? You're just adding zeros or subtracting zeros, so we don't care. So it's okay, you can just ignore those terms and get a new series that's not going to differ from the original one, but without those 0 terms, okay? So this is not really something too bad to assume. So we have a series and all the terms are different than 0. Then what you're going to do is the following. you're gonna consider an plus 1 over an. It's gonna be an expression, right? And you're gonna take the limit of that. So you will take the absolute value and you will take the limit of that. That limit is gonna give you something. You will either get a number or infinity. Okay? One of the two things you're gonna get. So if you know how to compute limits, you're good here. You're either gonna get a number or infinity. Depending on what the limit is, you can immediately say what happens to the series. If the limit happens to be a number less than 1, then the series converges absolutely. If the limit is a number bigger than 1, including infinity, then the series diverges. If the limit is 1, you're out of luck. You cannot use this. The test is inconclusive. You need to do something else. Okay? But at least if you compute this limit, and if you get a number that's different than 1, you will be able to say, if you get something different than 1, you will be able to say something, whether it converges or not. Okay? So this is a very nice test. The ratio test is inclusive. Let me say here, do something else. Okay? Do something else. All right. I'm going to do examples now. Do you understand the statement? In the examples that I'm going to do, they're going to reflect the type of series that you may want to use this. The type of series that this is very effective. This is very effective whenever you see factorials. You know what factorials are?
Yes.
Okay? Whenever you see factorials or exponentials, this is very effective. If you don't have those, it could be a little bit iffy, because then the point is that you want something that you can nicely control this ratio. And with factorials and exponentials, this simplification is very nice. With others, it's not so nice. Give you an example. So, determine convergence. And remember, when you use ratio test, if you get convergence, you immediately get absolute convergence. Okay? Not just regular convergence, not conditional. You will get, if it converges, you will do so absolutely. Okay? This is a very powerful test. All right, so let me put here sum from 0 to infinity, 2 to the n over n factorial. So when you see factorials, you immediately, ratio test should be in your mind. Also, when you see a bunch of exponentials being thrown around like this, ratio test should be in your mind. Okay, and then let me throw in here a number 4. Find values. This is to give you a hint of what we're going to be doing in the next chapter. Find values of x for which this series converges. Okay, this is an example of what we call a power series. Okay, so here we have 4 series. Our job is to study this. Okay, and see whether they converge or not, and so on. So let's see. Let's take a look at the first one. Solution. So for the first one, we have the sum from 0 to infinity of 2 to the n over n factorial. Okay, so this is my an, right? And because I say a factorial, that's a hint to use the ratio test. So I'm going to use ratio test. So I'm going to be using the ratio test here. And the ratio test tells me to look at the absolute value of an plus 1 over an. Okay? That's what the ratio test tells me to look at. And then whatever I get here, I take the limit. Okay? But it's nice to compute this first, and then we take the limit. Notice that here the series everybody is positive, right? So the absolute value really is not doing anything, so we can just ignore it in the next step. The absolute value is there in case that you have negative stuff, just to make sure that everything becomes positive, okay? All right, so what's an plus 1? That's 2 to the n plus 1 over n plus 1 factorial, and then an is 2 to the n over n factorial. Yes? So let's simplify this. So this is, okay, so you will understand why I'm doing this in a second. So remember, this will be times n factorial over 2 to the n. You have to flip the second fraction. Now, the first fraction, I'm going to prepare it for simplifications. So 2 to the n plus 1, I will write as 2 to the n times 2. The reason is because I want to cancel it with this 2 to the n. Okay? So at 2 to the n plus 1, I will write as 2 to the n times 2. And this n plus 1 factorial, so remember, this is the product from 1 all the way up to n plus 1. You can write that as n factorial times n plus 1. Do you understand this? If you don't, make sure that you review your factorial algebra. Okay? So n plus 1. So the definition, in case that some of you don't remember and don't want to say it because you may be shy, let me just write it here. So n factorial equals 1 times 2 times 3 times n minus 1 times n. Okay? It's a product from 1 all the way up to n. If you look at this piece right here, that's a product from 1 all the way up to n minus 1. You can rewrite that as n minus 1 factorial. Yes? So n factorial was n minus 1 factorial times n. So that's a recursive definition. Okay? For example, if I ask you to simplify 100 factorial divided by 95 factorial, how do you do this? You cannot use a calculator. You put this in the calculator, you get an error. This is too big for the calculator to handle. So you have to do it by hand. So how do you do this? This number is bigger than this. This is the product from 1 to 100. This is the product from 1 to 95, right? So that means that this guy will simplify with all of this, and there will be a tail left over. What's the leftover tail? 96 times 97 times 98, right? So 100 factorial, you can write it as 95 factorial times, just complete it. Right? And then this is gone, and you get this. You understand this? So that's what I just did here. It's just that I did n factorial times n plus 1. Okay? And why did I do that? Because now this is gone, this is gone. So we end up with 2 over n plus 1. Yes? So the ratio test says to consider this limit. Right? We need to consider this limit, so that will be the limit as n approaches infinity of 2 over n plus 1. What is this limit? 0. In particular, what do we need to do with this limit now according to a ratio test? We need to compare it with 1. Depending on what we get, then we make a decision. How does this number compare with 1? It's less than 1. So what does the ratio test tell you when it's less than 1? It converges absolutely. Now, the absolutely part here is really a redundancy because a series is already of positive terms. So if it converges, you will do it absolutely, right? But it converges. So, converges. We good here? So, the first one converges. And if you want, you can say absolutely, but it's really a redundancy in this case. Did you understand how we use the ratio test? But the next one, what was the next one? The 3 to the n. So again, I'm going to use ratio test. So I'm going to look at the absolute. Okay, so it's absolute value of an plus 1 over an. I don't need the absolute value because everything is positive here. Okay, so I'm going to do an plus 1. That's n plus 1 squared times 2. Do you understand it's to the n plus 2? Because it's n plus 1, right? Over 3 to the n plus 1. And then, if you don't mind, I'm going to already do times and then flip the second fraction, okay? Are we okay? All right. So, again, to prepare this for simplifications, this guy stays here. Now, the 2 to the n plus 2, I will write it as 2 to the n plus 1 times 2, right? Why? Because I want to cancel it with this guy. And the 3 to the n plus 1, I will write as 3 to the n times 3. So, this is gone. This is gone. So, what do we obtain here? On the top, we have 2 times n plus 1 squared. And what do we have on the bottom?
3 times n squared.
3 times n squared. Okay? So what is this limit as n approaches infinity?
2.
So the limit as n approaches infinity is 2 over 3. Does everybody see this? This is a rational expression, right? You can think of this as a rational function. The leading, so degrees are the same. Degree is 2, so it's a ratio of leading coefficient. The leading coefficient at the top is 2, because this is n squared plus 2n plus 1, so it's 2n squared. So it's 2, and the bottom is 3, so the limit is 2 over 3. Okay? Or you can do L'Hopital's rule, whatever you want. The point is that you're going to get 2 over 3. Once again, less than 1, what can we deduce? Convergence. Okay? So converges by the ratio test. Do you understand this? For example, if instead of a 2, if that would have been, let's say, a 5, something, a 5 to the n plus 1, then you have a 5 here, right? That's very different, so the limit would be 5 over 3. It would be bigger than 1. What would be the conclusion? Divergence. Okay? And then, I guess, for this one, for number 3, okay. For example, I see this and I wouldn't even use ratio test. I would just use alternating series test from the get-go because I see the alternating symbol. But the point is that if you do ratio test, I believe that we're going to get 1 for the limit. So let's do that for practice. So if we look at the absolute value of an plus 1 over an, that's just going to make everything positive, so I will get rid of the negative 1 to the n. So basically, we're going to have square root of n plus 1 over n plus 2, that's an plus 1, times flip an. Yes? So that's going to be n plus 1 times this, divided by square root of n times this. What is this limit as n approaches infinity? The degree of the top is 3/2, right? The degree of the bottom is also 3/2. So once again, the limit here is going to be the ratio of the leading coefficients. What's the leading coefficient of the top? It's a 1. The leading coefficient of the bottom is a 1. So when you take this limit, you're going to get 1. That means that the ratio test doesn't tell you anything here. So ratio test does not apply. All right. So we cannot use it. It's inconclusive. But you need to do something else. What can we do? Alternating series test. Just look at this. What's the limit of this? Not the negative 1 to the n. What's the limit of this as n approaches infinity? It's going to be 0. N grows faster than square root of n. Yes? This limit is 0. And for the same reason, because this grows faster, when n is big enough, these terms are going to get smaller and smaller. So this is decreasing. Again, you can sit down and argue, etc. But the bottom line is that this converges by the alternating series test. So it converges by the alternating series test. Now, how is it? Is it absolute convergence or is it conditional convergence? Why?
Because it's only when it's being alternated, it's not when it's absolute value.
I mean, to tell me what condition, you need to argue that the absolute value diverges. We haven't argued that. Well, if you consider this, and this is a good example. If you consider this now, this is what you get with the absolute values. Yes? That this converges or diverges. What test would you use to analyze this?
The P series, you do the n to the 1/2 minus the n to the 1, and then you get.
So, but what test would you use?
The P series.
You use a P series, but what do you use? A comparison with a P series. Limit comparison test, right? Use a limit comparison test. So we're going to compare limit comparison test with the P series. What P series? N to the 1/2, right? 1 over the square root of n. So that means that we're going to take the limit as n approaches infinity of this guy over 1 over the square root of n. And we know that this one diverges, okay? And the point is that this would be, when this goes to the top, we're going to get a square root of n times square root of n, so that's just n over n plus 1, right? So this limit is equal to 1. Now be careful, okay? Ratio test is the one that has a problem with 1. Limit comparison test says as long as you get a number bigger than 0, you're good. So you have to make sure that you have that clear so you don't get these things confused, okay? We're doing limit comparison test now. So this is bigger than 0, so the series diverges. So since this diverges, P series with P less than 1 equals 1/2, then this series diverges as well. So it converges, the original series converges by alternating series test, but now we know the convergence is conditional, right? Conditional convergence. Okay, questions? Yes.
So when it says that the ratio test does not apply, does that mean that if it could converge? Absolutely.
Yeah, you cannot deduce anything.
Okay.
It just means that if the limit is 1, then move on and do something else. You cannot say anything.
Right.
That's what it means. Yes. Okay. Questions? Do you understand this? So I didn't have time to tell you anything about the root test. So I guess, but the root test is actually the same as the ratio test. It's just instead of taking the ratio, you take an nth root, and it's the same thing. So you look at the limit of the nth root of an. So you look at this limit. Okay, this is L, and again you play the same game. You compare it with 1. If it's less than 1, converges absolutely. That's so valid. If it's less than 1, converges absolutely. It's bigger than 1, diverges. If it's equal to 1, does not apply. Exactly the same thing as ratio test. It's just that it's called the root test because you take the nth root. Okay, that's all it is. Because you're gonna see this in the homework. Okay, I'm gonna write it in the notes. I'm gonna add it to the notes. But the way you use it is exactly the same as what we did here. It's just that instead of looking at a ratio, you're gonna look at an nth root. Okay. Now, when you compute this limit, typically you will need to use this. Typically, you will get this type of things like 1 to the infinity or infinity to the 0, that kind of stuff. So you will need to use L'Hopital's rule, right? The techniques that we discussed some time ago. Right? As e to the ln. You know what I'm talking about? Talk about this like 3 weeks ago, 3 or 4 weeks ago. I think that's what I wanted to say. And that's it. If you want, I strongly encourage you to just look at this because this is a very strong theorem. So you need to wonder how does this work. And the point is that by having that limit, we managed to get this type of inequality. Okay, that limit guarantees that the absolute value of n plus 1 is always between these two quantities, and therefore you will be able to bound your series with a geometric series. Okay, that's why 1 is so important, because 1 is going to be the ratio. Okay, so we can bound our series from above with a geometric series. If this is less than 1, then this converges, therefore that one converges. Okay, and we also have a bound from below with a geometric series. Okay, so if this is bigger than 1, then this diverges, therefore this diverges. Okay, that's the gist of the core of what's happening inside this ratio test. But anyways, this is just for your general knowledge in case you are interested. You just need to be able to use it, and it will be very important for us. We're gonna use it next chapter. Like almost every lecture that we do starting next week is gonna point to the ratio test. Okay, so it's very important.